Everyone say hi.
Hi.
So now we all speak. All right. Today we're going to be taking a look at 4.1, the introduction to simulating and experimental probability. So that is in chapter 4.1. Now, let's start with this. What are the chances that it will rain tomorrow? What's that?
Weather guy says.
Depends on what the weather guy says. Okay. Is that all we need to do? Just check in with the weather guy or CP24 and then that's that?
Will they look at like around this time of year? No, not that. They look at like the clouds and stuff.
They look at the clouds and stuff. Okay, good. Good answer. Good answer. With the clouds. All right. What else? Air pressure. Okay. So look at clouds, air pressure, wind speeds. Okay. Good. So they have all these numbers that they're looking at. Okay. Air pressure, wind speeds, clouds. Right? No, I do. Satellite imagery of the clouds. Which is essentially data that they sort of put together and try and come up with an understanding of, well, is that going to affect the chances of rain tomorrow or the next day or 5 days from now, and so on. And really what we're talking about when we ask questions like this, what are the chances of, we're talking about probability. What's the probability of it raining tomorrow? They usually give you a percentage. 70% chance of rain, 33% chance of rain, and so on. We talk about the likelihood of an event happening. And that's what we're covering today. We're going into the discussion of likelihood. And what are the chances of an event happening and determining the probability number around that. First thing we'll take a look at is, okay, well, if we're trying to answer that type of question, how can we answer that question? What sort of tools or methods that we have at our disposal to figure that out? And today we'll talk about running experiments or simulations around that. All right, let's talk about fairness for a second. In a game, what makes a game fair? Rules. Okay. Rules? Yes, Julian?
Recalling that game equally. Like, I don't know, if it's not one-sided.
It's not one-sided? Okay. So there's sort of a balance there, or an equality there, yeah?
If all participating parties in the game have an equal chance of winning.
Yes. Good answer.
That's awesome.
I didn't see your eyes shooting. That's good. All participants in a game, excellent, have an equal chance of winning. And there are things that are in place to make sure that happens, like rules. Okay. Pretty good, pretty good. The game is fair if, okay, first point, all players have an equal chance of winning. And so there's no decided advantage on either side in that game. Also, we consider, what about this scenario? If all players have an equal chance of winning, okay, then could it be said that each player can expect to win or lose the same number of times in the long run? Meaning, if you keep playing this game, and if you're telling me that all players have an equal chance of winning, and you keep playing it and playing it and playing it over and over and over again, looking at the results of wins and losses over time, if I'm a player, can I expect to win or lose the same number of times as time goes on?
Yeah.
Yes? Okay. Now, why is that?
Because you're all equal, having equal chance.
Okay.
of
Okay, because we all have an equal chance. You're right. So, um, I guess it's essentially things have a way of working themselves out if they're equal, averaging themselves out. If there is no clear advantage, then it may be fair to say that you can expect to win or lose the same amount of times as time goes on. So that's when we talk about fairness. Okay? Is there equality? Okay, does everyone have an equal chance of winning? With that said, then let's take a look at a scenario for a second. You'll see a lot of product placement in today's lesson. Let's take a look at a scenario here. If, for instance, myself and let's say someone else in the math department, we decide that, okay, well, every morning we'll come in and, we'll flip a coin, okay? I'll call it. If I'm right, then, they buy the coffee for the two of us, right? If I'm wrong, then I buy the coffee. Okay, let's consider that scenario for a second. And some other details around here. So if I call it right, then they spend $2, okay? And I obviously spend nothing because they spend $1 for a cup of coffee each. And if I lose, then I end up paying $2 to cover the both of us. Okay. Flipping a coin, is this a fair game? 50-50. Okay, so looking at the nature of flipping a coin, you have two sides. Hopefully that it's a regulation size coin. So it's fair. There's no advantage either way on either side of the coin. Flip it up, whatever side it lands on. That determines the winner of that particular game. 50-50. Everyone okay with that? Everyone says, yeah, okay, I'll buy that. Sure. Okay, so if that's the case then, how much would you expect to spend on coffee in a 5-day work week? $4 to $6. Okay, that's good. It's a good range. I like that range. So sort of cutting it right down the middle. All right. Okay. Anyone else? 5-day work week. Considering this scenario right here, how much can I spend in any given week? $4 to $6 over there. Yep.
Maybe you can spend up to 10 because then you can be against you every time.
Okay, so you could spend up to $10. So you're having a bad week, not calling the sides that week very well. Although I don't know if you can call it very well. You just have to call it. But luck isn't on your side, so you lose every game that week. You end up spending $10 on coffee for that week. Okay, you get a winning streak that week, and you end up calling every day, calling it right. What do you get? 0. You win 5 days in a row. Okay. So, if I wanted to, let's say, if I wanted to budget, if I'm looking at my budget for the month or for this term, and I want to say, okay, how much should I set aside every day for coffee, or how much should I set aside in 1 week for coffee? How can I plan around that? What number would make sense for me to set aside for coffee on a weekly basis for the term? $10.
No, 5. And then
5?
like you can have it like come from like last week you only had to buy 1 coffee. This week you have to buy 4.
Right. Okay. Okay. So that's certainly a one way of looking at it. So if I just set aside 5, and given that it's 50-50, I might have an off week 1 week, but I might have a good week another week. So that $5, okay, $5 1 week, $5 the next week, all depending on how I do, it could end up working out.
If you have a bad week, you should.
Yes. it's true. If you do have a bad week, then you are quote screwed. Um, well, let's say but we're talking about overtime now. I just want to sure you might have a bad week, but over time, what's up? You're gonna have good weeks too, as well. So, you could set aside $10, every week. But that's certainly playing it very safe. But then also, um, if things have their way of evening out, you could have some money left over as well to do other things. But for the sake of argument or answering this question, would it make sense just to set aside $5 for that week, from week to week? Okay, so let's keep that in mind for a second. Now, what if I wanted to test this theory and say, okay, well, is this game fair or not? One way that we can do it is, well, because we're just flipping coins, we don't have to wait till you're actually getting into it and just wait day to day to keep flipping coins with whoever you're playing the game with and seeing whether or not it's fair. You can just go in there and set up an experiment to see, okay, well, let's just work this out and see if it makes sense, if this is a good deal or not. And you can just map it out and go through the trials yourself. Conduct an experiment and essentially just simulate how things are going to be from a day-to-day and week-to-week business. So here we have a chart right here to model that. So who wants to call it? All right. So if you call it, you're calling it for me, let's say?
Okay. Heads.
One win for us.
Heads. Heads. Selena. Heads. Idiots. Heads. Oh, I won.
All right, so
They like bothering you. Oh my God, what class is this? What are you doing here? You should know this, eh? You should know this.
I know it's easy.
Mm-hmm. See you.
I was just walking through.
all right, so here we have 3 wins on a bad week, 2 losses. So on this particular week, okay, we have 2 losses there, which ends up in spending $4 on coffee on this particular week. Okay. Is it enough to say, okay, well, look, I tried it out, I mapped it out, and yeah, I came out on the on the positive side of things. Yeah, it's fair. Let's do it. Is it enough to settle for this one experiment? No? Okay. How much further should we go?
Like 3.
Three,
Best out of
four.
5. Best out of 5.
Best of 5? Okay. All right.
Best out of 5.
Well, I guess is there a limit as far as how many times you could do it to simulate? No? Well, I guess theoretically there isn't. You can keep trying it over and over and over again, and you'll get various results. But in the end, I mean, we talked about it. In the end, because we know the nature of the game, it's 50-50. theoretically we know that things are going to even out. If you keep playing this game over and over and over again, this cost on a weekly basis is expected to be around $4 to $6. Okay, which if you just take the middle of that, you can probably guess that your weekly budget for coffee is going to be around $5 over time. Here's what I want you to do. If you said that this isn't good enough for me to just settle on this right here, you each have one of these worksheets.
I have one.
Where's the whole
With a partner, please make sure that you have a coin, one coin between yourself and your partner. One person flips, the other calls it. And what I want you to do is where it says who's buying coffee, I want you to fill out the charts there. And we'll do this for the next 10 minutes. We'll see you are at the 5-minute mark. And we'll go from there.
Oh wait, I want the other one.
You have a coin? Loonies and tunes. All right. That's a loony for you. Yes. We'll go to the next. Ooh, that's a, I don't know if that's a flip. That was a drop. Okay. Did anyone come out severely on the losing side of it? Yes, yes. Some of you. Is this game fair?
No.
No?
It is fair.
No?
It depends on what.
What's the most that you paid in any given week?
$8.
$8?
$8.
10? That's what. Better check that coin. So we had some $8, $10. Anyone go on a crazy winning streak? Yes. Anyone have a $0 week? Oh yes, there we go. It's right there. Yeah, that's right. All right. So I think you guys get the point. If you, you can simulate a game like this, given the exact, what we just did right here. We're taking a real scenario, coming up with a model around it, like you see here, and simulating the game and getting a feel for the likelihood of things. Let's go through some terms for a second. What you just did, right, in this experiment, first of all, one coin toss, okay, we can call that our trial, which is one repetition, okay, of an experiment. Tossing up the coin, catching it, somebody calling it, checking it, that's one trial. Random variable, okay, a variable whose value corresponds to the outcome of a random event. So in this case here, in our little coffee game, the cost of, the daily cost of buying coffee, was the result of the outcome of the game. But that value is random. Okay? It could be 0 one day, it could be $2 the next day. Okay? 0 the next day, 0 the next day, $2 the next day, and so on. Whatever that value is, daily cost of buying a coffee, that's going to be a random a random value. When we talk about discreteness, okay, a discrete random value, does anyone remember what the word discrete means? I think grade 9. What's that? Not? Yes, what is not obvious? Okay. Yep, that's certainly one meaning of being discrete. Sort of secretive about things, I guess. That's one meaning of it. In a mathematical sense, there is another term for, or another meaning for being discrete. If you take a look at the word continuous, what does the word continuous mean? Over and over. Keeps going and going and going. So if I take a look at a something like a variable like time, time is an example of something continuous, and that time just keeps going and going. And if you break, you take each individual unit of time, okay, let's say 1 second, you can break that further into milliseconds and so on and so on. At any point, that variable, you could, put your finger on it and say, and take a value from it. You can get sub-values. That's what we mean by continuous. Okay. When we talk about being discrete, we're talking about actual units that you just count. Okay. You have, you win 1 coin toss, and you win 2 coin tosses. There's no such thing in this case as playing half a coin toss. Okay. When we say discrete, it's items that you can count. So if I say, for instance, I have here 2 pencil cases, right? 2 discrete values. 1, 2. You can't have 1.5 pencil cases. Right? If I could have 1.5 pencil cases, somehow magically there's like half a pencil case in between them. That's continuous. All right. Sorry. That's continuous value. But we're talking about discreteness, concrete, solid values, items that you can count. Okay. When we talk about discrete random variable, okay, a random variable that has a finite number of possible values. Okay. In this case here, the daily cost of buying a coffee is either going to be 0 or 2 on any given day. It's not going to cost you $1 and $1.50 the next day. It's either going to cost you 0 or 2, all depending whether or not you win or lose that game. So that's what we talk about being discrete. And whether or not it's 0 or 2, that's completely random. And that's a random variable. In any given experiment, you could have an expected value. So, given the nature of an experiment, if you play it over and over and over again, what the expected value of it should be. In this case, all you're really thinking about is, well, what's the average, or what's the mean? Since the total cost of coffee in a given day is, in any given day, could be $2, okay, the expected value for your daily coffee is $1, because it could be 0 or 2. So over time, you can say, well, for 1 day, I could set aside $1 because if you average out, between 0 and 2, you're going to have 1. So that's what we talk about when we talk about our expected value. An event, okay? In an experiment, you have an event, okay, which is basically a set of possible outcomes of an experiment. Winning a coin toss is one outcome of that event. Okay? Losing the coin toss is the other outcome. Okay? Each one of those is a separate event. and here we have a simulation. So it's essentially what we just did here, is an experiment that models an actual event. Okay? We didn't have somebody else from the math department standing here next to me, and we didn't just perform it once today and say that's it. Okay, that would be the actual event, where we're actually have it on the line. Right now we're just simulating it, and that's what we did. We just spent the last 5 minutes doing. Okay. How else? Okay, given what we just did, how else could we simulate? Is there any way of getting a feel for whether or not this game is fair, okay, and sort of running an experiment that would simulate the same sort of scenario? Is there anything else that we could do?
Is it only just in this game?
Yep. Yep, so that's one form of simulating it.
Rock, paper, scissors.
Rock, paper, scissors.
Dice. So like with coin.
Okay, with dice. Okay. Rock, paper, scissors. Well, depending on what kind of dice you have essentially
One dice.
one dice.
Rules like.
Or a card. Okay. So, what's the one? If you were to simulate this game, what's the one thing that you have to keep in mind, whatever tool it is that you use?
You have to have 50% chance.
Okay, good. So whatever it is you choose, you have to have a 50% chance of winning that game, and obviously a 50% chance of losing as well. Here's another method right here, which is you can essentially use technology. Here I have a spreadsheet, okay? And all I've done is, on the spreadsheet, you don't have this, you don't have to write this down, I just want you to look at this. In each one of these cells, okay, there's a function that I'm using called rand between. And basically all it's doing is giving me a random number, okay, running all calculations in the back and just spitting out randomly the numbers 0 or 1. And so basically what I've done is, I've set aside my 5 days in the week, set up 10 trials right there, okay? So this is another way of simulating an event using technology. And we'll probably get into this, a couple of days from now. I'll have to decide when we want to fit it in, but we might get the calculators in here, and you can do this same sort of thing right here in terms of simulating an actual event. Okay. All right. With that said, then, we're taking a look at the probability of events happening. Probability is really a measure of how likely an event is going to happen. So a measure of the likelihood of an event is called the probability of that event. So it's basically the question, answers the question, what is the likelihood of winning a coin toss? It is based on how often a particular event occurs, okay? How often a given event occurs based or in relation to, or compared to the total number of trials. Okay? What's the probability of winning a coin toss, okay? The event of winning a coin toss compared to the number of trials that you go through. And essentially probabilities that we get from experimenting, well, they're just called experimental probabilities. All we're doing is running an experiment, observing, keeping track, okay, of wins and losses, and deriving a probability from that. This takes us to this. This leads us to the definition of experimental probability. Okay, so experimental probability is the observed probability. What you guys just did, you observed, you kept track of wins and losses, okay? The observed probability of an event A, okay? So when we see our formula here, this A, that is the event that we're looking for, okay? The observed probability of an event in an experiment. And looking at this formula, here we have our probability, okay, represented by P, okay? The probability of event A occurring, okay, is calculated by the number of times that A occurs over the total number of trials. So if we put this into context of what we've just done, so the number of times, the probability of winning a coin toss, okay, which is our event A, winning a coin toss, can be found by taking the total number of wins that we get over our number of trials. And when we do that, on the bottom here, probability is expressed as a number between 0 and 1, because this number right here at the top is always going to be less than or equal to the total number of trials. So we can say that in terms of probability, okay, based on your observations, what is the experimental probability of winning a coin toss? Looking at your sheet right now, counting up your wins and losses, what is the experimental probability of winning a coin toss? Expected to be 0.5, yes. Based on what you observed, though, what is that number? So look at your sheet right now. How many wins did you get over the number of trials? Okay, so 0.64 over here at the back. Pretty good number, 0.64. 0.64 over here. 42. That keeps
I do have it one more year. Yeah, I
work
for that every day. And you have to just work 10% school.
real number?
And there's one where
It is a real number.
Yes.
and there's one where
Real in the sense that it's
color the color less spins.
fractional. That's
They pay
what
Yeah, you put $5 $5
Right. And obviously you're at, yes. So we have a 0.66 over here. We have a 0.4 what? 0.42. 0.42. Okay. Basically what you're doing is you're taking we're looking for the probability, experimental probability of winning a coin toss. You're going to take the total number of wins over the total number of trials, the total number of coin tosses. You take that, and that gives you your experimental probability. Count up. I don't think you can count both. I think you count up how many times you won over the number of times you flipped. That's what we can. What's that? What's your number of times I've won?
Well, it depends which way you do it.
Yeah, it's every time you win over. We're looking for the probability of winning.
35 because we only did 7 trials. 5 times 7 divided by 35. How many
I'll give you a
You guys did all of this? You have to do it by divided by 50. How many times? 6, 3, 6,
Okay. Let's put a wrapper up. Put a wrapper on this. We are still recording, all right? So we have a couple of minutes of dead air there for a bit. I'll have to fast forward that part. Just have like people talking about your 0.42 probability.
Yeah.
All right, so guys in the back. Just to take a look at what we covered today, so we know that a game is fair when all players have an equal chance of winning. Okay. When we're talking about probability, we're talking about the likelihood of a particular event happening. Experimental probability is determined by, okay, we observe, and then observe the number of occurrences of an event over its number of trials. And experiments that model actual events are simulations. So we went through a simulation today. Sort of coin toss as well. Homework again. This is posted online, but just so that you see it here, I want you to read example 2 in the book. It's under batting averages on page 207. Do these questions right here. So 209, 1 to 3, 5, 8, and 13. And then also the check-in question on the website. Yes.
My notebook goes from like page 134.
Yeah, I noticed. I know there's a sort of a something that jumps right in between, but I think, yeah, I noticed that too. You shouldn't lose any pages. It's just that, yeah, I think in your book there's like 2 pages in there for that particular chapter. I don't know why.
I did get a book.
You did get a book.
I'll-
We didn't get